Hi, I'm Omar, and this is my work with SBOL Industrial Summer Program Internship under the supervision of Thomas and James. We are working on SBOL3 support for DNAplotlib. We are trying to build version 2 of DNAplotlib to be able to draw SBOL3 visuals inside the data files. Let me explain to you what we have done during these last 3 months. And let's go. First of all, I have used this project board by GitHub to do the tasks and manage them, order them, and send emails and put links and this stuff. So it's good to use. And the other thing, we contacted using the email and a weekly Zoom meeting. And let's go ahead and explain what happened in the project. Here in the README, as you can see, the installation is straightforward. You just need to put the DNAplotlib 2.py file in the Python path, and you are good to go with import the library. The internal data structure, which we have changed during the first month of the internship, now can support a complex biological designs like different backbones and molecules interactions. And the rendering part, this is the class we are using to draw the glyphs. This class contains integration with by paraSBOLv library and matplotlib in order to draw the glyphs. So you need to install these three first to work with the library. Of course, by SBOL3 to deal with SBOL files, and I'll let you how in a minute. And let's talk about the features available right now. You can create a byte design manually or and draw it. You can sort the different components inside the backbone according to the start range on the sequence, the location of that part on the DNA sequence. You can order them. Also, you can build a hierarchical architecture of the different backbones, like having a component, and inside a subcomponent, and inside that a subcomponent and other subcomponents. We can flatten this and draw it as a different backbones. Also, you can draw molecular species, even created manually or inside an SBOL file. And finally, of course, you can read the SBOL file and sort the parts inside it according to the start range also and draw it. We have integration with SBOL3 to read SBOL3 files and translate the components inside it to the DNAplotlib2 data structure, which I will explain it now. But first, let's have a look at the final results of the diagrams we have. These two are created manually by me. You can create a file and use the data structure of DNAplotlib2 to add these components. Like this is parts combined in a backbone, and this is an interaction between these, and you can draw these using the renderer class. This one created from inside the SBOL3 file. You can send a specific object or component you need to draw, like the object 5 in the file, and it will draw it for you. And also you can draw a complete component inside the SBOL3 file. This one should be two backbones, not like that, because we have a small bug in finding the subcomponents attributes. So for now we are drawing it as a separate component, not a subcomponent. So it deals with these as a separate one, but some of them related to each other. We'll fix this as soon as possible. And also molecular species can be drawn, as you can see. And the sort algorithm works well. You can control the ordering of this stuff by hand if you create it manually, or in the SBOL3 file using the start range on the sequence. I will show you the code and how it works. Starting with DNAplotlib2 file, which you will find in the DNAplotlib2 directory. This file contains 7 classes, 5 of them for the internal components of the SBOL3 file to store the components, and this by design one to collect all these stored ones in order to draw them by one command. And the last one is the renderer class, which will be used to actually draw the components with integration with paraSBOLv library. So first you need to import the paraSBOLv in order for this to work, and also the SBOL3 as we are gonna use document and SBOL3 files. Let me show you the part class, which is the most important thing here, as we draw using the data inside it. The part type and the SO term is the most important things. We have a map to map the SO term found in the file to the glyph type we are gonna use in the paraSBOLv to draw this part. We have the start range here, which is the range location of the sequence on the sequence DNA. We can order using it. The result of this class will be a dictionary, this one. We get back this dictionary, which is the values and the keys and the values of it. These parts are the subcomponents, and we collect these inside the backbone, which is mainly a component or a main object. In this backbone, you just add the different parts together to make it on a separate line or on the graph. And we can do the same for the molecular species as well, the same as part. You get the name, the SO term and the type, and store it on a list. And then in the biodesign class here, you add this backbone one by one to be separate, and also the molecules the same way. After that, you go to the renderer class, and mainly here you have 3 functions: the get components, DFS, and biorender. Get components, we are gonna use it to draw a specific component inside the SBOL3 file, or all the components if we didn't send an index or a specific object to draw. Here we check if this is a valid component or not, and then check the variable we have called visited in order to use the DFS function, which is the second function in this class. This function gets back the backbone with all the subcomponents of it on a separate list. So we are gonna add these to the backbone lists, and this contains all the backbones. We are gonna go through the DFS right now, which we are gonna use to flatten the hierarchy of the backbone, find the subcomponents, and also find the molecular species inside it. After we check the validity of the component, we add it to the visited in order to visit it just one time, in order not to draw a subcomponent as a component once and a subcomponent of another component once again. So this helps us doing this. We check if it has a features or not. If it's not like this one here, that means it doesn't have a subcomponent. So we are gonna get its SO term, because it may be a separate component or a molecule to draw alone. We do this by searching for the SBO term and the SO term, and do a mapping between it and paraSBOLv glyph term map. Glyph term map have the SO terms and the glyph type, or just glyph type map, so we can do the map here and draw it. After we do the map, we create a part and give it this glyph type and of course the SO term name, and the name of this subcomponent, or sorry, this component, and orientation. Then add it to the backbone if it is an SO term or an SBO term. SBO term is most of the cases a molecular species, a DNA, RNA, or these things. We create the same thing as we did up here and add this molecule to the molecular list. If this condition doesn't work and it has already a feature, that means it may have a subcomponent. So we are gonna loop over these features, these subcomponents, and check if they have a role or not. This role contains the SO term, and when we find this SO term, we are gonna use it to do mapping like the above one. But here the difference is this is a subcomponent of the component up there. Then we create a part of this and add it to the backbone, and finally we call the DFS again with that subcomponent this time to check if it has another subcomponent inside it, or it is the last one on the hierarchy. And we keep doing this to flatten this object we have sent using the get components function up. So these two functions work together to flatten the hierarchy of the paraSBOLv. After that, we have the biorender, which we send by design object. This by design contains the backbones, molecules, and interactions, everything. We use it to draw our glyphs. We check if the molecular species not equal 0 because by design created automatically, but with a length of 0. If we add another molecules, it will not be 0, so we are gonna get these molecules and draw it. After that, we sort the backbones according to the start range using this line. We sort the backbones, then we loop over every backbone and check its parts and draw them one by one. And finally, we have our graph drawn. This is how the internal data structure of DNAplotlib is able to draw complex diagrams, different backbones and molecules, interactions between them. I will show now how to do this. I'll give you an example of file created manually and another one working on the SBOL3 file. Starting with the manually one, the easy one, render by design file, also found in the same directory. First, you create these parts manually like that. You give it its name, but this time you need this part type to be correct, because the SO term here is not used, as we are not gonna loop over an SBOL file. So the DFS function will not working in the manual part here. Also, you can specify the start range, which is the range on the location on the sequence, and you can edit these to change the output. You have created here 2 backbones, each one with 3 or 5 parts, and then add these parts to the backbone. Finally, add the backbone to the by design and call the biorender function. If we run this, you will get a result of 2 backbones like this. You can this is the first backbone and this is the second one. If we, for example, change this promoter, we can make it go after this terminator one. Let me do this promoter of the second backbone. I'll make it 6 to be bigger than this one. And if I run again, you find it go to the end. Make it one as it is. This is you can also do this for interaction or molecular species. You can add whatever you want manually here. The most important thing here is the SBOL3 file, so let's go to it. First, you create the SBOL3 file and read the document, read the .nt file to work with, create a renderer, and then this call the function get components. Of course, this function also exists inside the renderer class, but it has some bugs, small bugs, but it works from here right now, so we are gonna use it. If we send an index like this one, it will just create it. Let me run this like this one. Okay, you can change this as you want to draw a specific backbone inside the file. Okay, and finally add this molecule or backbone to the biodesign, and last step is to call the biorender. So the thing here to do is just correct this bug and find a way to get the SO term after we access the subcomponent. If that works, it will be corrected as a 2 subcomponents. Let me delete this and draw all the file here. Okay, this file should be 2 backbones and a molecule. The reason it works like that, because the subcomponents are not drawn here as a subcomponents. We draw it when we find it as a component, because we can't get the SO term of a subcomponent. There is no link between the same object when it is a component and a subcomponent at the same time. We can get its attributes using the component, but not the subcomponent. If we correct this, this will be automatically corrected to 2 backbones and a molecule, and also will be sorted. And that's all for now. Another thing I need to edit is these test files, where these test files of the renderer is not complete yet. We need to complete this. And here's the SBOL test cases. You can find it in a different directory, and you have the test cases and the code used to create each one of these. You can use any one of these and try it yourself. And that's all. And I think that will be too long, but I'm happy with the result, and I think we did a great job. Of course, we can improve this. We can support the interaction. We can also add a node and other things, but I need to learn a little bit more about the SBOL file to know how to access SO term from a subcomponent and this stuff. And I really enjoyed these things, and I want to thank my mentors for their support during the way. Of course, this cannot be done because without their help. So I will continue contribute to this project until we reach a good step. But for now, it's working, and we will make it better in the future. And thank you.